Yeah. Thanks. Yeah, that slide is useless.
Oh, wow, it's a great slide. Sure.
Oh, yeah.
Yeah, I mean, it's still recording on your PC, but
Yeah, because I plugged it in, so I didn't switch off. That's it.
yeah, exactly. But it should be fine. I'll sit here. Well,
Wherever you want.
yeah, because I want to check the messages if there's some issues, but let's say I'm gonna just sit next to you and try to observe. All right.
Okay. So, some review, maybe some new stuff to someone. Yes, so we look at Rn. We don't really care about other spaces on this course. Everything is real value. If n equals 1, it's just the real number, axis, one-dimensional axis, and then for higher n is the familiar Euclidean space. Just please raise your hand if something is unclear, something is new, something is, I might assume, or on the other hand, if it's like too slow and easy, then just tell me about it as well. So here's an example of a vector. It's 4-dimensional, n equals 4. And we will be speaking about row vectors and column vectors. So this is a row vector, first one, the second one is the column vector. Do I have the pointer? Can I point? I will point like this. Okay. So it's just a matter of convenience. The reason is because we are talking about matrices. These are actually special cases of matrices. So this is like 1 times 4 matrix. This is 4 times 1 matrix. And for things to be coherent, it's convenient to have this difference between column and row vectors. And instead of wasting space like this, we can also just put a little t on top, so it means that we're looking at the transpose, which is the column version of that. And we will always assume by default that vectors are row vectors. So then we will always put the t if we want to transpose it. So okay, so row vectors can be multiplied by a column vector in this way, and this is what we know as a dot product. So it goes coordinate wise. So the first coordinates are multiplied, second ones are multiplied, etc., and then we sum them up to get the answer. At this point, I can remind you that if anybody finds mistakes, they get points. I tried not to put mistakes. I thought of putting on purpose, but then I didn't. So there should be no mistakes. But if you find then just email me and or tell it right away, and then we'll give you points. Okay. So why is dot product interesting in machine learning? Is because as we spoke already last lecture, it directly models what happens in a neuron once we simplify the neuron down to basically a linear integration of input. So we have this activation of previous neurons, input neurons, x1, x2, x3. And their activation is fed into this neuron on the right side to get the answer, which is y. And these activations, these inputs from x1, x2, x3 are weighted by these different weights, w1, w2, w3. So what we get is that the input from the first input will become w1 times x1. And the intuition, like if you remember this biological biological metaphor, these neurons are connected to this one by an axon, and the axon is always the same input, but the position and the geometry of the neuron can affect how much the signal decays before it actually impacts the cell. And that's the weight which tells how strongly or weakly this signal can become negative in our model, not necessarily in biological neurons. There are inhibitory connections as well, so maybe. And so then when we sum them up, and that was another simplification that we make in computational science, is that we assume that all these signals are simply summed up instead of some complex integration. And then the result is y, and as we can see, the same thing as product between these two vectors. Okay, a matrix is an element of n times m dimensional space, and usually represented as a two-dimensional array like this. So the number of rows is the first number, and the number of columns is the second number, which is kind of reverse from what we are usually doing when we have a coordinate axis. We first look at the horizontal axis and then the vertical axis. With here, it's the opposite, just to make things question. Okay, so somebody's asking online that is dot product seems to reduce the effect of individual weights. Is there a way to overcome this? I'm not sure why does it reduce the effect of individual weights. Is it because there are many of them? So for example, W1 is, yeah, they get summed together. Well, the thing is, so for example, W1 will tell us how much X1 will influence the final result. If W2 and W3 are small and W1 is big, then the influence of X1 is big. And if they're all the same, then their influence is the same. So yeah, if there are like millions of these neurons, then they get lost. But that's actually what we want. We don't necessarily want to overcome that. I hope that answers the question. Yes. So here we have a matrix. 3 times 4. We might call n the output and m the input dimension, but I'll probably confuse them, so I'll try not to do that. But that's apparently a common way of speaking, because you multiply it from the right. On this course, we will tend to multiply matrices on the right, so then it will make sense this way. Okay, so a matrix can be multiplied by a vector from the left, by a row vector. It has to have the same dimension as the number of rows. And the way it's done is that we take dot products with each column. So the first number is the result of taking dot product with the first column. Second number is the result of taking dot product with the column. Third, fourth, and so on. And we also multiply matrix from the right, and then we take dot products with the rows. So this is what I mean when I said that this is what we're going to do usually. So the first number in this case will be there's a mistake in this slide. I'm not going to say what it is. Okay, so I take the dot product with the first one, second one, the third one, like this. This is how you get the answer. Did anybody notice the mistake? 3, 4.
So under this thing.
Oh, online. No,
Output dimension is wrong.
output dimension is correct. Because well,
N dimension wrong.
right?
N dimension wrong. Well,
Yes, n is 3 and m is 4. Three times 4 matrix, 3 times 4 output. Right. I mean, as this, that's not the. I call them this because I'm assuming that we always do the multiplication from the right, right? So, okay, is there some problem here? Yes, n is the output dimension. What I'm saying here. Yes, we obtain the n-dimensional vector because that's the output of this. That's not the problem. It's kind of a small mistake. Okay, but you.
Common, but
Yeah, okay, so Sebastian gets 3 points. This should be column vector. So I should have put the T there. So, okay, good. Please write me an email so that I know.
in the camera.
Camera.
Point
There.
something for the camera.
Right. Whoever gave this, Sebastian, please write me an email so that I know who you are, and then I will give you 3 points. Okay, so why matrices are important in our endeavor? Because, so we just saw that, so here is correct, right? So here is, we get the column vector. When we multiply it by column vector, matrix by column vector from the right, we always get a column vector. So as we saw, the matrix multiplication is just a bunch of dot products. And as we saw in the first couple of slides, each neuron produces a dot product. So when we have a neural network like this with 2 layers, then we have dot product, dot product, dot product. It's exactly the same thing as matrix multiplication. I'm not gonna now have this yellow things because it's kind of tedious to do actually. But you can imagine that this times this would be that. This times this is this. And we sum them together and we get y1, etc. So neural networks will be essentially, if we don't use any activation functions, which we will, and soon we will understand why it's necessary to use activation functions. So before that, matrix multiplication. So we not only multiply matrix by vector, we can also multiply matrix by matrix. What has to happen is that the dimensions match. Well, in this case, all dimensions are just 2, so it's boring. But if we have a matrix which is 2 times 3, we can multiply it by a 3 times 2 matrix, or 3 times anything, in fact, 3 times 4 even. No, doesn't matter how many, as long as it's 3 rows here and 3 columns here. The columns of the number of columns of the first one has to match the rows of the second one. And here it kind of makes sense to call them input and output, because the output of this matrix has to match the input of this matrix, because this is actually a composite function, which we'll see in the next couple of slides. So when we multiply, do I have this visualization here? Yes. So this is also a bunch of dot products. So the first, in some sense, we can look at it this way, like this. So this vector is this matrix multiplied by this vector. And then this column is this matrix multiplied by this vector. So it works like this, but you can also look at it one by one. So this number three there on the right is the dot product of these two vectors. This number is the dot product of these two vectors. This is the dot product of these, and this is the dot product of these. This is how we get matrix multiplication. And we can also add them up. So when matrices have the same dimensions, exactly, all dimensions have to be the same, then we can add them up. We just coordinate-wise add this. I actually have a visualization of that as well. But, so this plus this plus this.
I think there's a mistake. 1 times -1 is -1. It would be.
Here?
Yeah.
Let's go back.
That one.
Yeah, that's correct. Thank you. Send me an email, please, and you'll get a. It was, yeah, I was trying to be careful, but but I missed that one. Okay. So why matrix multiplication is interesting? If we have a more complicated neural network, what happens is actually when we take this matrix that gives us this first transition, and then the matrix which gives us the second transition, then in fact, from X to Y is the same thing as taking the matrix product of these two matrices. You can check it out. It's not difficult, but it's kind of, well, if you want to write the general proof, then you will be drowning in summation signs and indices. But you can do it, and I think last year we did it, and maybe I will put it in the notes. But it also is kind of obvious once you understand how all these dot products work and stuff. So if this matrix is here, this matrix is here. So then if we multiply these matrices, we get something which is like V times W, another matrix. So then we could replace this entire thing with just that matrix. We'll do the same exact result, which shows us that, in fact, no matter how complicated your neural network is, if we don't do any activation functions, so here we're not, so this H1, H2, H3 are nothing. They don't do anything. They just take the sum weighted by these weights and spit out the answer. They don't apply a step function. There's no sigmoid, no nothing. And when there is no activation function, then it's indeed just matrix multiplication, in which case it never pays to have a more deep or complex network. It's completely useless. This can be replaced by one matrix. And that's why activation functions are necessary if we want to have any advantage of having a deeper network. To have anything else except a linear function. Linear functions are very useless in machine learning. Like, no, that was wrongly said. They are very useful, but they are useless if you only use them. Okay, matrices have basic properties. These are linearity properties. Okay, I'm missing T here. Nobody saw it, so nobody gets. I was faster than anybody. I get 3 points. Okay, so this is familiar, right? You can open the brackets. This is called, what is it called? It's called distributivity. That's what it's distributivity laws.
Yeah. In the fourth row, is there an n after the equal sign?
Oh, there should be an M. Yeah, you're right. Same thing. This should be an M. Thank you. Copy paste mistake. All right, so if we have here we should have a column. So if we have a matrix, it always defines a function because we can always take any vector and multiply, so any vector from the correct space and multiply it by that matrix, and then we get a new vector, and so this defines a function. For each vector, we get a new one, so it's a function. And this function, by the properties that we just saw, is linear. And conversely, any linear function between any Euclidean spaces can always be represented by a matrix. That's a little bit less obvious maybe. So linear functions are defined like this, that they satisfy precisely those distributivity laws. And the kind of beautiful thing about linear algebra is they are 100% correspond, in finite dimensional spaces, they 100% correspond to matrices. There's obviously also linear function theory in infinite dimensional function spaces, but that's much more advanced stuff, and it's called functional analysis. But for finite dimensional spaces, these correspond exactly to matrices. So the converse is not so obvious, but it's proved in linear algebra course. If you're interested, just go to the mathematics department, wherever it is, or read online, ask ChatGPT. So yeah, so that's what we get. That's what we get on this. That if we have neural networks without any activation functions, every node is performing a linear function, then no matter how much you put them together, you always end up with a linear function. So that doesn't really help. So we need activation functions, but that's not the focus. Today's lecture, today we are going to be looking at computational graphs. So we want to analyze what happens in more general setting when we take composite functions, as if some slide is missing. Example 1 is missing. Okay, example 1. Maybe I will draw it. So, but then I need to stop sharing my screen. Yeah, but example 1 actually I gave last lecture kind of already. So the simple example, if I have a function let's use just one dimension. Two functions, and I can take composite function, and I can represent this in a computational graph like this. This is my way of representing this. Technically, I will have a node here representing the variable. I will not have a node here for mathematical reason, because this is the function basically. So whenever I have a node, I take the previous output from the previous node, I apply the function. So I already have the output result. And then this spits, if there is an output connection, then it spits out the answer. And then this one takes in whatever came from there and applies that function. This is the computational graph version of this. So this is a very simple situation. Now, as we saw, if these are linear, then this is linear, but now we don't assume that they are linear. So in this example, and from now on, I'm assuming these are just any functions, probably differentiable functions, but for now, it doesn't really matter what they are. the second part of the lecture, they have to be differential. Now I want to share the screen. Awesome. Okay, second example. So here we get something more complicated. So now we have a function g, which takes two variables. So then we have two functions f1 and 2, and we aggregate them in this way. So whatever these functions output, we put this one as a first coordinate, as a first coordinate into G, and this we put this as a second coordinate into G. So one may ask, how do we know which order? So if we just have this graph, how do we know which order do they come in? And this has to be specified. So actually, when we define mathematically these graphs, we have to order the nodes so that we know which is which. But in computers, they're usually ordered anyway, so it's not an issue. So this is a graph representing this function. Then we can have kind of a converse situation where we want to split the usage of a variable into many different functions. We did it obviously in the matrices where one input went into many different other nodes. The way we deal with it, so to make things mathematically simpler, we don't have functions which have multidimensional output at all. Instead, we have this dispersion function. So this dispersion function, the only thing that it does is it copies the same variable. Actually corresponds well to the biological neuron, where the axon always spits out some fixed output. It might branch. So this is the branching. And yeah, this is how we use the dispersion node. And thanks to the dispersion node, we don't, as I said, we don't need to have any functions that have multidimensional output. We can always replace them with those, using those dispersion nodes in an appropriate way. Don't need extra points. Okay, fine. So let's have another example. Now we have a linear, so example, a linear function. We can represent it like this. We can just put the function itself there. Okay. We can actually put any function there. So why do we need computational graphs? We just put the function there. So we have always a graph of one node. Well, we need it because sometimes we want to decompose, deconstruct the function into simple parts. And so in the case of this linear function, which is given by a 2x2 matrix, so it's a two-dimensional object. And as I said, I want to deal only with one-dimensional outputs. So to achieve that, I can decompose this matrix, this linear function like this. So I have the first input, I disperse it, so I use the dispersion function to put it there and there. And for the second variable, I do the same. And then these are now the component-wise linear subfunctions. So these are the corresponding to the rows, the first and the second row of the matrix. But I can further deconstruct this same function and open up those dot products with the rows of the matrix, and then I will denote them like this. So in the previous slides, I put the weights just on top of the arrows, but that is not mathematically general enough to account for all possible functions. So instead, I now replace those multiplication by this constant by a separate function. So now I have a function which actually the only job of this function is to multiply the input by this number A. Recall the matrix was A, B, C, D over there. So the only function of this M, A, function of the function, purpose of this function is to multiply the input by A, purpose of this function multiplied by B, C, and D. So in this way I can represent this function as a computational graph. Now there's no way to further simplify it. This S is summation function, so it doesn't do anything except just sum up the inputs, and the same here. Yeah, and in the previous notation, I can write it like this. Yeah, we can have these more complex graphs where there's a skip connection, like this one. However, we can always assume that there are no skip connections if we need it for mathematical reasons, because you can always put a dummy node in between. So in fact, we can prove that any computational graph which is built up from functions and dispersion functions can always be modified without changing the function so that it's layered. So it has very structured layers, meaning that if we start with some initial nodes, some final nodes, and then the graph can be partitioned into this very nice layer so that each layer always feeds into the next layer. This layer feeds into the next layer, and so on. So we never really need to use this kind of skip connections. So connection to machine learning, everybody knows, I guess, that we speak about layers in deep learning networks. That's how they're organized. That's how all the libraries usually work. Keras, TensorFlow, you just add layer by layer. There is also a notion of skip connections, actually. I don't remember where are they used. The truth is, mathematically speaking, we don't have to assume, even if you have a skip connection, you can always put these intermediate nodes which don't do anything. So what I'm putting here is the identity function, which just takes the variable and puts out the same variable. And then in this way, we can replace any graph with a layered version. Similarly, the dispersion, we don't really need other than the double dispersion and the signal, which is the identity, because we can always replace it like this, right? So instead of dispersing the variable into 3 parts, we can always have it dispersed twice into 2 parts, and then again. And so we don't really need to use this more complex dispersions. This will be handy when we prove things about backpropagation. Okay. So now let's move, I'm moving kind of a little bit backwards. So I gave you a lot of examples, and now I want to go to the more mathematical theory. So in general, we speak about directed acyclic graphs. And I spoke about this already last lecture. What does it mean? These are directed graphs where cycles are forbidden. Cycles are forbidden. Doesn't mean that there are trees. Somebody might think that when there are no cycles, then it's a tree, but not in this case because we don't count this as a cycle. Let me show it now. We don't count this as a cycle. Why? Because the direction of the arrows matters. So we count as a cycle only when the arrows go really around. And if we have a cycle, then it's very problematic to compute the value of a function because it's never ending. So we spoke about it last lecture. Okay, here's a anatomy of a directed acyclic graph. This is a nicer way to present things. Like typically in mathematics, I would list like definition after definition, but you can just show pictures. It's much more. It's nicer. So okay, so we have what? In every directed acyclic graph, there are initial nodes. The definition of initial node is a node that doesn't have any parents. What is a parent? The parent is a node from which there is a connection to the node. In this case, for example, green node has 4 parents, which are purple or blue. And then there's final node. Sometimes there are many final nodes. A final node has the opposite property from the initial node, which is that doesn't have any successors. And whenever we reverse a directed acyclic graph, we get another directed acyclic graph. So we could reverse the direction of every arrow. So then this becomes the initial node, this becomes the final nodes, and the children parents reverse. And this is what we do when we do backpropagation, which we will do later today. Okay, so given graph which is labeled by variables and function symbols, we can given like if we have algorithms that compute each of these functions, then we can compute the entire graph. And I don't have a visualization of that, but the way it happens is that we assume that we have some values for these initial nodes. And that's why they are always labeled by variable symbols. So we have symbols for variables and we have symbols for functions. And we assume always that initial nodes always get assigned variables. Other nodes are always assigned functions. And what we do, so they're assigned. And now then every node kind of sits there and waits until all its parents have been computed. And once all its parents have been computed, then it computes its own output. So for example, this node G2, right in the beginning, already one of its parents is computed because it's the input node, so there is already some value. But this node still waits because these nodes F1, F2, F3 are still indeterminate. In the next time step, F1, F2, and F3 compute their output because F1, all parents of F1 are settled. That's the only variable F1. All the parents of F2, X1, X2 variables are settled. So all of these 3 nodes can compute the output on the first time step. And after that, G2 suddenly realizes that all its parents now have been computed. So it can compute its own output. Same with G1. So on time step 2, G1 and G2 compute their outputs. And time step 3, H computes its output. And we have the output of the entire function. 3 time steps, even though we have much more many nodes. And this is the power of parallel computing. And the reason it's possible is because we can do this locally. So as I mentioned last time, one of the principles of neuroscience is that neurons don't need to know what other neurons do. And it would be kind of demanded too much. They don't have cell phones. And or radio transmissions. It would be cool if we evolved the radio transmission, but we didn't, or so we think. So we think, at least, that's how we model, is that the neurons act independently. And especially when we do the layer thing, so we remove those skip connections by adding these dummy nodes, it becomes all very structured. So then we don't have, none of those nodes needs to weight anything. We always know which nodes already can be computed if we don't have these skip connections. So if I added this dummy node here, then I will make sure that the whole thing is layered, then I can always know for sure that the next layer can be computed from after the previous layer, then the next layer, the next layer. And now, if you imagine that these functions are linear functions plus some activation function, that part which is linear is very easy to do with a GPU. It's because it's a matrix multiplication. There's like well-known algorithms how to parallelize them precisely for this reason. And so GPUs are very good at parallel processing. Normal processors were never built for parallel processing. Why is F1? Yeah. Didn't I say it? Maybe I didn't say it, but it is. F1 goes, what does it mean F1 times 1?
Because F1 is an input of G2, and
Yes.
is that not in the functions? Yeah,
Oh.
it's not. G2
Oh,
doesn't
boy.
take F, it takes X2 directly.
I
Oh,
forgot.
but no, that's true.
X1.
Yeah, so you didn't put F1.
Yeah, you're
It's a
right. It was a mistake. Last year, during the entire course, only 3 people used this opportunity. So I'm really happy actually about this. Good.
And an email.
Yeah, whoever send this message, please send an email. You need points. I mean, I know there are some people following this course who are not planning to get credits. So then you don't need. So here's the algorithm for those who like algorithms. Should we take a break? Let's take a break. Or which one do you prefer? Take a break or okay. So let's look at this algorithm. Kind of, we already looked at it, but we'll get a computational graph. So B is a set of nodes. B is the edges. And C is the assignment of functions and variable symbols to the node. So C is a function from so C is a function from the nodes to some set of functions and some set of variables such that the initial nodes are assigned variables, all other nodes are assigned functions, and we have some of the functions are the dispersion functions and some other functions. And right in the beginning, we already assign values to the initial nodes. So whatever, this is our graph. So here we have these are assigned value right at the beginning. Then we define the intended result are the values in the output nodes. Right. This is what we want to obtain. And then the algorithm runs like this. So we form a set, which is the set. The idea of this V0 is that that's the set of nodes which already have been evaluated. At the beginning, the nodes that are already evaluated are the initial nodes. So those which don't have any parents. And then as long as this V0 is not the entire set, so as long as there are any nodes which haven't been yet evaluated, we repeat this loop. And in this loop, we have a for loop where we just go through all the nodes and we check if the parents of the nodes have already been evaluated. If all the parents have been evaluated, then we compute the value. So what's happening here is that we take the function, the C of that node, that's the function which has been assigned to it. And then we put in the values of the parents. And here's a mistake. So this W should be V's. These enumerate the parents of V. And then we add that node. So we computed it, so we add it to the set already computed. And then we repeat. But note that this for loop can be made in parallel. So there's no reason why this has to be consecutive. All nodes can be just waiting on their own for the input, and once they receive all the necessary input, they produce the output. And yeah, and another thing, in fact, this if we have this layered network and whatever, we don't have to compute the parents, so we don't have to look for which nodes are which parents, because we're going to make sure that if the network is layered, then just one step at a time, all the parents of the next layer's nodes are computed, and that's how this becomes very efficient. But it's not obviously efficient because computers were never designed to be parallel, this is the reason why we're using GPUs for machine learning. It's so strange. GPU, what is it? Graphics processing unit was not designed for machine learning. It was designed for gaming, in fact, to play games with high resolution visual stuff. And then I remember when they suddenly realized, oh, we can use it for machine learning. Then Google produced TPUs, which were designed for machine learning. But that's the thing, our brains are by design parallel, but computers are not. And that's what we have to adapt a little bit. Okay, well, why do I have this slide here? Uh-oh, I have it. All slides are missing. Maybe not.
We send it. See.
I don't care. We can do it on. We'll continue here. I don't need the. Yeah, I don't need the. This, and I don't need it at all. Let's switch it off.
Do we need to?
Yeah, if I
Oh, you
use
want-
this,
that's it.
so we'll put the camera. I have is so small.
Yeah, that's small.
technical program, move on to the old school.
Actually, no, they have a much quicker way to fix this. So student.
Okay, so as we spoke last time, the secret to machine learning is finding derivatives of these complicated functions. So we have, it's not much use of having a complicated function if you can't control what it does. Let's have, just for the sake of simplicity, only one output, and maybe even for simplicity, let's assume that we have just only, okay, but no, we can have several inputs, but only one output. And we would like to take derivatives. So let's start with asking how could we differentiate this function by reducing the problem to differentiating only the functions which are at the nodes. Because eventually we will see that we can put only very simple functions here. The sigmoid function, the rectified linear unit, and we know how to differentiate them. It's very easy. And then by using those, we can then differentiate these very complex functions. So the idea is to use the chain rule. So let's remind ourselves what a chain rule is. I'm trying to think how I'm going to use these boards. Perhaps. Okay, so a reminder. And I will always use the big phi because I denote the entire function given by the graph by phi. And suppose I have some function inside of big phi, and I want to differentiate it with respect to x. And last time we already figured out that it's given by the derivative of f times the derivative of phi and with the input. And if we have more complex situation, namely, we have that the big phi is actually two functions. Has two inputs, which are then both dependent on x. How does this derivative work? Well, it's also a chain rule. If anybody has done vector calculus, we take the derivative of the inner function, which in this case is a function with a two-dimensional output, so it's a vector. So we will actually here I would save space by writing a column. We have the derivatives of this. Let's get up space. Well, yeah, but it's kind of okay. Yeah. Yeah, so technically should have it a row vector. This and then dot product with the gradient of phi. And where do I evaluate this phi? I evaluated it at the original points. Okay. Is this something that people have encountered heard about. It's just a generalization of this. It's the change. And then we have two more important generalizations. One is, what if I have some other constants in there? So in the first situation, I might have that the f depends also on some other variables, but they're actually constant. And maybe this big phi depends on some constant, but this actually doesn't matter because they're constants. So actually this function is exactly the same thing. So we just take the derivative of f. But in this case, because f now is a multivariable function, we will take the partial derivative of f with respect to the first variable. And then we multiply by the partial derivative of big phi also along the first variable. And we put the constants in. So this is exactly the same as this. I just added the constants and then I replaced the derivative with partial derivative along the required axis. That might, of course, be not the first variable, could be the second or third, in which case I would have the partial derivative with respect to the respectful one. And then same thing with this, we could add constants in there, and but it would look exactly the same. I would just have to take the gradient carefully along those variables which are being used, and the rest are not used. So this is enough to prove the general, to kind of understand the general setup for the backpropagation situation. I have to say, I've never seen anywhere a complete proof of this. Rojas, one of the books on our list, claims that he has a proof, and he has a proof in his book, but it's somehow incomplete. There's something missing in that. So I'll try to write in our notes complete proof of this backpropagation thing. Okay, so we will proceed by induction on the size of the network. So suppose we have a network which has just one node. So then let's make it bigger just for everybody. Suppose we have a network with one node. So we divide it into two parts. And okay, one node, one input, one output, one dimension. So then it's very simple. We have a function here. We put its derivative there. And the way we obtain the derivative at some point is that we first do forward pass, forward propagation. That's what we did in this algorithm. We go from some variable, we get the result, and meanwhile we store. This node stores what was the value of this variable when it was put in. Let's put it here below the node. So it stores it here. And when we do backpropagation, it applies this function, this derivative to this. And so it puts back this. So that's it. One node, very simple. If we have one node but multiple inputs, now I need to erase. We have one node and we have multiple inputs. That means that this function is a multivariate function in many variables. This f, that's something like f, x, y, and z. So it has three partial derivatives. We can take a derivative with respect to x, with respect to y, with respect to z. If somebody not familiar with this, it's very simple. So suppose we have like some function like this. If I take the derivative with respect to x, then I treat this as a constant. Then it's just we take the derivative of x, and this is a constant, so nothing here, it doesn't change. If I take the derivative of the same function with respect to y, then I treat y as a variable, everything else is a constant, so then it's just this. The y disappears because I take the derivative with respect to y. If I take the derivative with respect to z of this same function now, I treat this as a constant. And then this z is a variable, and now I get this, right? So just so that everybody is on track. Okay, so we have functions, 3 variables. We put the partial derivative with respect to the first variable. Put it like, technically I'd like to put it like this. I divide this node into 4 parts. One part, which is the function output, so it collects everything in outputs. So in this case, it's x1, x2, x3 instead of x, y, z. And then here I have this partial derivative with respect to the first variable, partial derivative with the second variable, partial derivative with respect to the third variable. And now I do exactly the same thing. So when I do the forward pass, I put in some values here, and I compute the value there. And at the same time, I store. Question? No. At the same time, I store. So this node has a little memory, and it stores these values which were passed forward. And in the backpropagation step, we put in those same variables into each one of those. So we get the partial derivative with respect to the first variable, second variable, third variable. So when we combine them, we get the gradient of f. So it's the definition that if you combine the partial derivative into one vector, that's called the gradient. So we get the gradient because this goes out the first partial derivative, this goes out the second partial derivative, and this goes out the third partial derivative, and so together that's the gradient of that function. Okay, so one node.
Let me show the vector, because when you say combine together, it's
Yeah, sorry. So what is a gradient? Let's put it here. So what is a gradient? Suppose we have a function which has three dimensional input. The gradient of f is the vector first partial derivative, second partial derivative, third. So
that thing there, right?
it's that thing here and that thing there. Yeah. But this is different. So what's the difference? Here we have function which takes in 3 variables and puts out 1 variable. This pair is a opposite. It's a function that takes 1 variable, x, gives out 2-dimensional output. So then we have this. So we haven't even used anything there. I just proved this. It works for 1 node. So let's assume that we have proved that we have like some complex, induction. By induction, let's assume that we have this some kind of complex network for which we have already proved that when we do the backpropagation, I haven't even told you how we do well, actually, so how do we do backpropagation? The algorithm is that, I guess I should first tell you what the algorithm is. Okay, so here's the algorithm. We have a network. Each node, first we do the forward pass. Each node does what it does. It takes in whatever was put in it, and it outputs the output, and it stores the value of the variable that was given to it. Or if it was given two variables or more, then, okay, so this function here takes two variables, and here we have the partial derivatives. Now this function will store both variables that were put in. And then here we have again a function which just takes one input. It stores that one, and each node does the same thing. So imagine this continues forever. So this node, exactly the same thing. So here's some function, I don't know, f1. And here we have the partial derivative of f and another partial derivative, and it stores whatever values came out from the previous nodes. And you can denote them by O, like output. It stores them, and etc. Each node does the same thing. And then when we have completed the forward pass, we do the backward pass, and each node takes whatever it has stored and plugs it in to those derivatives that it has here. So this function f will, now we reverse this whole graph, and the information flows backwards, and now there is something coming into this node. What does it do? It takes the input, multiplies it by what it gets when it applies this derivative to the stored input. So take the derivative, apply it to the stored input, and multiply by whatever came in, put it, and then spit it out. Each node does the exact same thing. This one, it had two variables stored. There is a backwards pass here. So what it does, for both of those, so for the partial derivative here, it plugs in both stored values and multiplies by this, whatever number is coming from the right, puts it there. And here it takes the second partial derivative, applies to the stored values and multiplies by whatever came from there and spits it out here. And what does a dispersion node do? Dispersion node simply collects whatever comes from. So by the way, I assumed that in my graphs, and I showed you that without loss of generality, we can assume that all nodes have only one-dimensional output, except for the dispersion nodes, which are purposefully there to account for that. So this is why we don't need to care what happens when there are many different reverse inputs. Only one. So then we just multiply each one of those by the same number. But for the dispersion node, the rule is very simple. When there are, in the backpropagation step, there are numbers coming in, all it does is just sums them up and spits them back. This algorithm will always produce, in the end, here, the partial derivatives of the entire function with respect to this variable and with respect to this variable and all the rest which are here. So it will give you the gradient of the entire function with respect to these variables. How much time do you have?
15 minutes, 17 minutes.
Okay, so very nice. So let's look why this works. If I have just a linear graph, it's clear. Because what's this function? This function is h of g of f. And when I take the derivative, exactly what I do. So I take some number, I pass it forward. Here I store x, here I store f of x, and here I store g of f of x. Then when I do the backpropagation, okay, let's remind, we have always the derivative over here. So in the backpropagation step, the stored input gets put in to h prime. So what does this send back? It sends the number which is equal to h prime of whatever it has stored, which is g of f of x. Then this person takes that and multiplies it by what it gets when it applies this derivative to this stored value. So the stored value is f of x, applying g prime, we get g prime of f of x, and we multiply by this shorthand. And then that's the number that is being backpropagated. And then this person does the same thing. So it takes the stored value, applies the derivative to it, multiplies by whatever came in from there. So that's exactly the derivative. So because by the chain rule, right? So we have f prime times g prime of f of x times h prime of g of f of x. That's the chain. That's how it works. That's the algorithm works perfectly. So the important question is, why does it work when we have all these different connections?
I have a question. We just did
Yes.
this, but the dispersion note, isn't it that when you put in a variable tool, it just makes copies of it, right? And why do we sum them up when we get it in the back probability?
Because of this, how this works.
So it's again like a gradient.
Yeah, it's because yeah, we go gradient, but then we take a dot product, and in dot product, if you remember, we sum up. That's a good question. That's a good question, yeah. Okay, so let's see how we make ourselves convinced that it all really works. So imagine we have some function, and we know that the back, whatever we did, produces the correct values. So that's maybe there's some complex graph here. It could be just one node or more. For one node, we already proved it that it works. So we can do the induction hypothesis. So now I add a new node here. And I imagine that it's, so there are only two options. Either it's connected to one of them, or it's a dispersion node. So if it's connected just to one of them, all the arrows originally go forward, and then backwards. If it's connected to only one of them, then what does it mean? it means that as far as this is concerned, these are constants. These are some numbers that were fed up in the forward pass, some variables that went there, but they do not depend on this. So as far as this person is concerned, these are constants. So from the perspective of this, whatever is this entire function looks like this. So this is let's say this big phi, and now we have added the big phi of some variables x1, etc. And now we replace x1 with some inner function. So this is what happens when we add this. No, now there is some function f which is fed into there instead of the variable. So now this function looks like this. It's big phi, and inside we have f of x. Suppose it's some variable. More generally, there can be other inputs, but they're also treated as constants. It's this observation, but for the sake of simplicity, let's assume there's only one variable there. But this big phi, it depends on some other constants, some other variables, but from the point of view of this, it's a constant. So if I take the derivative of this with respect to x, I'm using the chain rule. So so the derivative with respect to x of this thing by using our chain rules is the derivative of x of f times the derivative of big phi with respect to this first variable. If it's this, then it's the second. If it's this third, doesn't matter. In this case, the partial derivative with respect to the first variable, and inside we put f of x and then these constants that there were five. By the induction hypothesis, our backpropagation algorithm puts out the correct derivative here. So it brings out this, the partial derivative with respect to the first variable, and then because in the forward pass it stored the value of f of x here, it puts it in there. So that's the exact thing here. And when this node performs the backpropagation by our algorithm, it takes that input, whatever was propagated, and it multiplies it by f prime of x, which is the stored variable here. So then we get the correct answer. So in this case, when we feed only into one of the variables, we get the correct answer. Perfect. So the most maybe non-trivial question then is, so what if we have a dispersion node and I purposefully told you that we can always assume that it's only two, it has only two branches, so we can actually assume the picture looks like this. So what does this mean? This means that here, by induction hypothesis, we have the correct, when the backpropagation happens, the thing that comes from there is the correct partial derivative of this phi. And here also the respect to the other variable. But this d is a very simplistic function. just takes x and copy pastes it into two parts. So now, if original function was big phi of sum x1 and x2, now the new function is actually just f, a big phi of the same variable twice. What is the derivative of this with respect to x? It's even simpler than, we don't even need this. Too complex. It's much simpler. What's the derivative of this function with respect to this variable? Oh, we're using this, but a much simpler version. Now we have f is just, in this case, f is just x and g is just x. So the derivative is 1. And when we have derivative equals 1, then we have the vector 1, 1 dot product with the gradient, which is the partial derivative of big phi with respect to the first variable and the second variable. And what is the dot product with the vector 1, 1? It's just the sum. Just the sum of these two. And this was the definition of the algorithm. So in the dispersion node, you just sum it up. It was Philip's question why we do that. So assuming that this algorithm up until this point was correct, so we get this and this. What this node does is simply sums up those. And we just saw that that's the correct answer. So then it propagates further, and that's correct. So now what we have done is that we have proved by induction on the complexity of the graph that no matter how many nodes, how many layers I add, I always, the nodes at the most leftmost, no, the initial nodes will always receive the backpropagated, the correct derivative. Okay, so I suggest that as an example, we have 5 minutes left, so we'll just do an example of this. And let's have an example which is somehow kind of machine learning like. I wonder if we have enough time. Let's replace the sigmoid by a sine function so it's quicker. We don't have to do all the acrobatics. Sigmoid. So let's assume that we have a function x. Then there is a sine. Okay. Sine. Here we multiply by 2. Here we have 5 minutes, so let's not make them more complicated. And here we just sum them up. Okay, so what does it look like if I write this normally? Sine of x plus 2x. That's it. That's the function. Kind of boring. But we only have 5 minutes, so let's not be too ambitious. Right? So sine, that's this part, 2x is this part, then we sum them up. That's okay, so let's take number. First of all, we can take the derivative. Everybody knows how it's done, right? The derivative of this is here. So let's take the derivative, but this algorithm only works at one point at a time. So what's our point? X equals 0. 0. So what do we do? Propagating 0, x equals 0. First, this stores 0 as we store it. Then we apply sign. Sign of 0 is, what is it? 0. So that thing sends 0 in there. And this also 2 times 0 is 0, stores 0, sends 0. Okay, output 0. Backpropagation. We have the summation function. What are the partial derivatives? It's 1, constant 1, and constant 1 in both directions. The partial derivative with respect to x of this is 1. With respect to y, also 1. So it doesn't really depend on the input. So it just sends 1. But backpropagated, 1. Backpropagated, 1. Then what does this person do? It has the derivative here. Applies the derivative to this stored number, cosine of 0, 1, times whatever came. So 1 times 1, that's sent back. Here, the derivative of this is 2. And it doesn't depend on the input because 2 is just a constant function. So this sends 2. And I forgot that we're not allowed to do this without a dispersion function. So we have a dispersion function here in the middle to do this dispersion for us. And what did the dispersion function do? Well, it simply sums them up. So it sends 3 here. So the result is that the derivative at 0 is 3. Correct. Hooray. And now add 1.8 trillion parameters and you get ChatGPT. So we're almost ChatGPT 4.
GPT-4, yeah.
So we're almost there. Okay, 6 p.m. So let's go home, and I will publish the exercises as soon as I can, but the latest on Friday. Next week, Friday. Next week, Nicoletta is going to be lecturing, so you will see me only in a month. So please don't drop out. Okay, good. Have a good rest of the day. Have a good Halloween if you're celebrating.
And also Friday, we don't have anything.
Yeah, this Friday, nothing. This Friday, exceptionally nothing. So.